concentrated more towards a standard norm of vector spaces. Okay, so yeah, okay. Is my screen visible?
Yes.
Okay, great. Yeah, okay. So what we are going to do today is the aspects of limits, continuity, and differentiability of functions which are multivariable functions. So most of these ideas are kind of very nicely defined in a calculus course. So a little bit effort in kind of a topological way or matrix space way is only required. Without too much of effort, you can actually extend these definitions. Most of them, okay, except the differentiability. I'll come to that. Okay, so what we are going to start with the idea of accumulation point. So if you have seen again accumulation point in the topological way or in sense of matrix spaces, you are already aware of this. So let's just go through the definition anyway. So what you start with is a subset of Rn, and you pick a point which need not be anything to do with the subset A. Okay, so it means basically that I will pick a point possibly that could go out of the set A as well. And then I'll say that this point is an accumulation point if for any positive real number, if I just draw a ball around that point, then that should contain, this ball should contain at least one point of A, the set A, other than the point X. Okay, so if you just look at this diagram picture below, you have a set A which is basically the all points inside the square except the boundary points. So don't include the points which are the black lines. And then of course if I pick any point from this set A itself, definitely I will end up getting this point itself is an accumulation point. That's no surprise. But if I pick this red point over here, which is X, which is lying on the right side of the square, so that is on the boundary, and I draw a ball around this or radius ball around this point, no matter what kind of positive real number I choose, I'll end up getting at least some point which is inside this ball other than this point X. For example, this green point over here, which you see, which is living inside this blue radius open ball. That's okay. So blue boundary open ball. So open means I'm excluding the points on the blue boundary. Okay, so this way I can observe a lot of points which are not in the set, which are also accumulation points, and usually those points are called boundary points of the set. Okay, so the definition actually much more stronger as we have seen in the usual real analysis. So if there is one point in that open R radius ball, then you can not just that particular point, you can get actually infinitely many points contained in A. Okay, so let's come to the definition of limit. So usually this is where the definition of accumulation point you would be needing. So you would start with a set A, and f is a function from A to Rn. Okay, so here also there is a problem. So you don't need this point little a to belong to this set A. Okay, so I can safely just look at a function from the set A minus the single point A to Rm. Okay, or if in case my A represents some point of A. Okay, otherwise I can just think of the A set minus A. So that means if it's not in the set A, then automatically it's considered. Okay, so under this consideration, just consider this function A to Rm, and if A is a point of A, then delete this. You don't need that at all. So then you say that the limit of fx as x tends to A is B, this particular vector, which is on Rm now on the other side. So the definition is kind of same as in calculus. Given any epsilon positive, there should be a delta, so that whenever I pick a point x which is belonging to the R radius, delta radius ball, open ball around A, okay, except the point A, then this should imply the norm of fx minus b, that is the distance between fx and b goes inside epsilon. Okay, in other words, my fx belongs to the epsilon radius ball around b. Okay, so again, in this case, we are just excluding the point x equal to A intentionally because we don't need to know what happened at the point x equal to A. Okay, in case f is defined at A, even in that case, this difference might not be. So for example, if I take x equal to A included in this particular situation, then it might happen that fx need not be equal to B for x equal to A. So this is kind of, again, the same kind of definition what you see in real analysis. Okay, so that is why, that is one of the reason I just want to avoid and this, and you basically need, there should be at least a deleted neighborhood where I can talk about fx. So therefore, it should make sense if, even if A is not an interior point, so you take some delta radius ball around A, then the deleted neighborhood of that ball should be contained inside A. That much at least you need. This is kind of hidden in this definition, which is already spelling it out in some sense. So we didn't need to write it, which is kind of assumed over here. Okay, so again, if I want to define, try to verify certain things about these, I can just invoke the sequential way because I'm working in a matrix space. So you take a function, exclude the point A to Rm. Then if I want to check that limit of fx as x tends to A is B, what I can do is that I should be able to verify that for any sequence xm, which is living inside these deleted set A minus A, and then I take the limit of that sequence, and that should converge to B. So if my xn converges to A without any of these xm's equal to A, or it could be slightly far, but still in that case, this limit fxn converges to B. This is the translation of the definition in the sequential form. This is sometimes easier because, again, using sequences sometimes give some easier approach. Okay, so usually, as in the case of real analysis, there is algebra of limits. So if you take limit of fx is b and limit of gx is c as x approaches a, then limit of fx plus gx should be the sum of their limits. And if you have a scalar alpha, if you take limit of alpha fx, then it should be alpha times limit of fx. If you take the dot product of fx and gx and take the limit as x approaches a, then it ends up being the dot product of the limit of those two individual functions. And same, if we just take the norm of this, norm of fx converges to norm of b as x approaches a. So these things is kind of routine verifications, playing with epsilon deltas, and you can easily verify this. Okay, so let's go ahead with continuity, and keep in mind this is slightly different from the existence of limit from at this particular point. Other than that, it's exactly the same definition. So here I need to make sense of fa. So that is why I need this a to be a point of a. So you take a subset of Rn and take a function from that subset A to Rm. You say that this function is continuous at that particular point chosen A if any given epsilon positive, there should be a delta, so that the delta radius ball around A under the image of F should go inside the epsilon radius ball around Fa. Okay, so in other words, you say limit of fx as extended to A is just Fa. So in this case, my limit coincides with the value Fa, and that is what is required. Instead of b, you specifically need my limit b should be equal to fa. So that's the only difference between these two definitions. And here we are not intentionally writing 0 less, because I'm already including x equal to a over here, which is easily seen as a part of the definition. Okay. Now, one of the interesting part is one of the first example you should encounter is that what happened to linear maps. Are they already continuous? So this is something which roughly has seen in the previous lecture, but there is a way to talk about continuity in terms of functional analysis approach, which is roughly we have done in the previous lecture, which I'm going to roughly go through over here. So in functional analysis, you say a function is continuous if and only if it's called, there is a term called bounded. The continuity and boundedness, these two are equivalent over there. But boundedness is some confusing property about the function. It doesn't mean the function values are bounded. It just says that the unit ball, closed unit ball, image of the closed unit ball of this function is bounded set. Okay, so this is what kind of seen in the previous lecture, in a sense that norm of Lx by x, norm of x is bounded by k, which is kind of we saw earlier. Okay, so here what you want to prove that L is continuous. So we start with some expression like this. We want to prove that this is continuous at A. So we start with this expression, and definitely because L is already linear, I can put them together and write it as L of x minus A, and make a change of variable to make it look like limit of LH as H approaches to 0. Now this makes my life easy in a sense that it says that I don't need to prove that it is continuous at an arbitrary point. I can just simply try to prove that this is continuous at 0. This is enough. So for this, what you do is you take the canonical basis U1 E2 AN of Rn. That means E1 is the column vector with the first entry 1 and the remaining entry 0. Second, E2 is only the second entry is 1 and the remaining entry 0, and so on. So if you take these vectors and take their norms, you take a max of that and define it to be k. So if I do this, the only danger is I may end up getting all these values equal to 0, all these norms equal to 0. So I wanted to make it positive, so I just thrown a 1 in that bracket to make sure that this k stays as a positive real number. Okay, so you take these max, and one of the calculation, not exactly in the same way, you can revise it to prove this inequality. Norm of Lx is less than equal to k times 0 norm of x. Remember, zero norm of x was kind of with respect to this particular basis, you take the sum of mod of the coefficients. And because I have a canonical basis here, the zero norm is nothing but the taxicab norm. Okay, so what I would do is that if I want to do this, we need to revise slightly, not too much. So you try to write down your x as alpha 1 e1 up to alpha n en as a sum, and then you apply the linear map L to that. What you end up getting is alpha 1 L e1 up to plus up to alpha n L of en. Okay, so the vector Lx is expressed in terms of these Le1s up to Lens. Okay, so there is another typo over here. Okay, so this one should be Len. Okay, so it is a linear combination of this. But there is one thing you have to keep in mind. I'm not claiming that Le1 up to Lens are the basis of Rm. Obviously, because I could take n and m to be different over here, or otherwise, even if they are same, I can take, for example, the zero linear map. So the proof should be encompassing everything. However, if I try to take a mod of that expression, mod of Lx, what you end up getting is norm of alpha 1, that is mod of alpha 1 times norm of Le1 plus mod of alpha 2, norm of Le2 up to mod of alpha n plus times norm of Len. So this is just triangle inequality you use. This is kind of what we did in the last lecture, and then invoke these max just to make sure that the k goes out of this, and what you end up getting is sum of those mod of the coefficients. So that is your zero norm over there. So this is how you get it. This is same trick what you applied in the last proof in the last lecture, the lemma around the end of the lecture what you saw. Okay, but this one more or less immediately implies that L is continuous at zero, in a sense that what we have already seen is that over Rm on the right side of the function, all the norms, because this is finite dimensional, all the norms are equivalent. So this zero norm of x, I can still bound it by something like less than equal to some k1 times norm of x. That norm is the standard norm of Rm. So if I combine this, I will get something like norm of Lx is less than equal to k times norm of x for a different capital K. But that is kind of much stronger than saying L is continuous. You just take these right side less than epsilon by k, then this term becomes less than epsilon. So this implies immediately L is continuous at zero. So therefore, every linear map already is continuous, and we'll see every linear map is also differentiable later on. So linear maps are something like nice maps where you can do everything. Okay, so one of the immediate applications of the techniques of the proof of these limit algebra over here, if you just apply it, then you immediately get something like this. If you have two functions f and g that are continuous at a particular point, then the sum function is continuous at this particular point as well. So for example, if you define some scalar multiple dot product and norm just defined like this, they turn out to be continuous at A as well. This is immediate consequence of these limit algebra and the definition of continuity over there. Okay, so far we encountered the definition of limit and the definition of continuity. Okay, and now what we are going to do is that let's try to look forward to one of the important theorem, which is almost immediate. So this is again in real analysis. You try to prove it happily. Compact sets are usually the closed intervals or finite union of closed intervals. Usually, of course, there are much worse compact sets you can imagine. But if you take those compact sets, then it's easy to see their images are going to be bounded. If in the proof of real analysis, the worst compact set you might have encountered is this Cantor set, and even then, if you take a continuous function, image of that compact set would be bounded. Okay, so here you see that again the same proof should work more or less. Image of a compact set is compact, which is proved as follows. Okay, so just quickly I'll recall what is compactness. Compactness in a matrix space is a set is called compact if I take it as covered by a union of open set, that is usually referred as a cover of the set A. Then I don't need the entire family of open sets to cover this. If it's compact, the definition says that I should be able to find only finitely many indices that still covers this set A. Okay, so just using this much, it's enough to prove that image of a compact set is compact. And what you need is, remember in the formulation of continuity in terms of matrix spaces, you just need the preimage of an open set is open. Okay, so let's start with if A covered by some open cover, V alpha. Each of these V alphas are part of Rm on the right side. And obviously what you need to do is that take the preimage of all those open sets, and using continuity they are all open sets in. Okay, so this is one question. This is not necessarily suddenly open in the set Rn, but you have to be slightly cautious. This is open in this set A. Okay, so what that means is that if you just restrict your attention to the topology of A, then it is open in that particular topological space. A could be a much worse set than how it looks like than open sets in Rn. Okay, but there is a way out. If it's open in A, then I should be able to write it as A intersection U alpha for a bunch of open sets in Rn itself. Okay, this is the definition usually of subspace topology. So a set is open in the subspace A if and only if I can express that open set as A intersection some open set in the mother topology over there. So my mother topology over here is Rn, and then I should be able to write this. Okay, that is good, because my F inverse V alpha now is a proper subset of U alpha. Okay, so I should be still covering A by the union of U alphas, and these U alphas are open inside Rn. And the definition of compactness is relative to the topology of Rn. So I should be able to cover A by those finitely many U alpha i's. So now I need to observe simply that my Fa is covered by union of V alpha i's. So whatever alpha indices you take, you just take the same indices corresponding to the open set V, and you should be able to see. But this is kind of very simple to prove. What you do is you take a point from Fa, write it as f of some point in A, and this point A should go inside one of the ui's, U alpha i's. The moment it goes in the U alpha i's, its image should go inside V alpha i's, because of the definition that U alpha is, because the definition if A contained in V alpha. So this is almost obvious from here, and therefore this point W should go in this V alpha. So therefore I ended up covering my set Fa as a union of V alpha i's. Okay, again, I'm going to use this mainly in the today's lecture around the end when I'm talking about the this composite of two functions when I'm applying the differentiability on them. This is usually called the chain rule in calculus, and here also we'll see something very similar, and I'm going to need that. And again, what I'm going to need also a compact set in Rn should be bounded, which I'm not going to prove over here. So the proof is kind of a little long, so I kind of would avoid this. Okay, so after this, let's come to the idea of derivative. So this is one of the trickiest point, how to generalize the derivative in higher dimension. Okay, so if you remember the definition of derivative in calculus, it just says you just simply, let's simply take a function r to r. You say that it is differentiable at a real number if a limit like this, which is much less harmful, if you want to imagine such things. So what you do is you compute the difference fa plus h and fa and divide by h and take the limit as h approaches 0. If this limit exists, and then you say that the derivative exists and you call it by f prime. The good part over real numbers is this limit turns out to be another real number, and you don't have to bother too much about what this number, how to represent this number in here. The problem in our dimension is that the derivative need not be a real number. It need not be a vector even if you take a function from Rn to Rm. So that is why you need to kind of translate this idea, what you exactly you are doing over here. So let's think about it. How do we define pictorially the definition of derivative? So let's say in this picture, I have drawn a particular function, the curve of this graph of a particular function. And then what you end up getting is that you look at the arc joining fa and fa plus h. As h approaches to 0, this arc kind of tends to become more and more like a tangent at the point fa, and this tangent line somehow represents the derivative at this point. So technically speaking, sometimes we have referred the slope of this tangent being the derivative, which is obviously true. Okay, so instead of generalizing to real numbers or vectors, which is not possible in higher dimensions, so what you can do is you will pick up this particular tangent at this point, fa, and this being a translate of a linear map, we'll try to understand these being how to define the derivative being itself a linear map. Okay, so what we do is as follows. So in this definition of limit, let's go to this over here. So this is equal to f prime a. So if I try to adjust a little bit, multiply h on the top of the other side and bring this real number on the left side, we end up getting some expression like this: fa plus h minus fa subtracted from f prime a dot h. So this product is a real product now. And of course, I can think of L f prime A being a linear map. Of course, this is linear, meaning I am bound to think of this being a function which passes through origin. So linear map is from R to R is always given by Lx equal to alpha times x for some real alpha, except if you stay away from the vertical line. That is also a linear map, which is you won't be able to realize that way. But still, if I just denote any linear map apart from the y-axis in this particular form, let's say I always get a real number alpha, and then this particular expression, I can simply write it as the linear map with slope f prime a computed at this particular value h. So this turns out to be same as the coefficient, the slope times h. This is what can be generalized in higher dimension. So in a sense, what you would do is you take an interior point of that particular set, then I call this function f from a to Rn being differentiable at this particular point A if there exists a linear map from Rn to Rm, so that I would be able to write it in a way that norm of fa plus h minus fa, and then you subtract this particular quantity in the higher dimension. This turns out to be lambda h, and take the norm, divide by norm of h, and take the limit as h approaches 0. So, okay, here there are too many norms over here, so you have to be slightly careful. The numerator has the norm coming from Rn, and the denominator, sorry, coming from Rm, because this numerator represents the value in Rm, and then denominator contain the norm coming from Rn. Okay, and then I can simply talk about this being a real limit, because if I take the norms, both of these are real numbers and I'm taking some quotient and I'm getting some expression. I'll just simply talk about what happens if limit h tends to 0, and I'll say that it is differentiable if this limit vanishes. Okay, but this is kind of little confusing, because in calculus the most important part was, it was almost immediate from the definition that if there is a derivative at some point, then that should be unique. Here in our case, the derivative is not just a point, but a linear function. Okay, so I get, the definition says if there exists a linear map. So the question is now, should I be able to ensure from the definition that the derivative is unique? The answer is yes, and which is not so difficult to prove. So what you do is you take a function f from a to Rm, and let's say I have two linear maps, both of them satisfy the condition given in the definition of derivative. Okay, I want to show these two linear maps are exactly the same. That will prove the uniqueness. Obviously, they are same when I put the plug in the value 0, because linear map sends 0 to 0. So I should be able to verify this when I take a non-zero point from Rn. So how do I do this? So you take the particular expression lambda h minus mu h and divide it by the norm of h and consider the limit of that. Okay, so instead of paying attention to the limit, you just try to pay attention to what happens inside. So in the top numerator, I can adjust it by introducing this extra factor fa plus h minus fa. Because mu h was minus, I'll just put it in the first, and then I adjust it with minus of minus lambda h over here. So this exactly is the difference, lambda h minus mu h. Okay, and then I use triangle inequality without invoking the limit, that this quantity inside limit is less than equal to the norm of the first one in the numerator plus norm of the second one in the second vector in the numerator. I still keep the norm of h in the denominator, and then I would be able to split it into two terms. Now limit formula says that if I take a limit of this, which is less than equal to limit of this, because this quantity was smaller than or equal to this quantity, so the limit should respect that. And then sum of two limits is equal to limit of the sum. So this is what the limit algebra says, which I can use it over here. And then the good part is the definition says both of them are 0. So therefore this is equal to 0. And obviously if I am taking limit of some non-zero quantity which is less than equal to 0, this would force that this quantity, which I started with, that has limit 0. Okay, so if this limit is 0, the what we started with, limit h tends to 0, norm of lambda h minus mu h divided by norm of h. So I should be able to write it in the more explicit epsilon delta definition. This is what I did. Take the deleted neighborhood around, sorry, take any epsilon positive. Then the definition of limit says that there should be a delta positive, so that if you pick all h from the deleted neighborhood with radius delta around 0, then this difference, then this expression should be less than epsilon. Okay, so that's directly coming from this limit is equal to 0. Now, this is simply not good enough, because the problem is I'm only focusing on too much around the deleted neighborhood of 0, which might be very, very small. Okay, and my equality should occur of lambda and mu should occur for all large enough points. Okay, large enough in a sense that all all vectors with very, very large norms. Okay, so for this we use a small trick. This is usually Archimedean principle. So what you do is you pick a non-zero point x from Rn, and Archimedean principle just says that because your norm x is any real number and my delta is positive, there should be a integer n, so that delta dot n exceeds this given any given real number. In this case, I am taking it to be norm of x, whatever large this norm of x could be. But this immediately says if I scale this x by 1 by n, so you take the 1 by n times x, it will tend to go inside or captured inside this deleted neighborhood of 0. Okay, now I am fine. So I should simply use, instead of h, this 1 by n times the vector x. If I just do this in this expression, what follows is that because lambda and mu are both linear functions, mod of 1 by n will come out of these numerator and denominator both. Okay, so if you just put it out, 1 by n is already positive, so they get cancelled. But if I cancel this, that basically means that I end up getting something like norm of lambda x minus mu x by norm of x. Okay, so this is less than, greater than, equal to 0 and less than epsilon. Okay, so what I started with is any arbitrary x, and my epsilon was here any positive real number. So what we ended up proving is that this particular number, norm of lambda x minus mu x by norm of x, is less than epsilon and greater than equal to 0 for every positive real number epsilon. That is only possible if this quantity itself is 0. But my norm x was non-zero, so I just put it up on the other side, and I simply get norm of lambda x minus mu x 0. So this immediately tells me that the value of lambda and mu coincides at the point x if it is non-zero, and of course they are equal at if x is 0. So therefore I get these two derivatives are the same, so they coincide. Okay, let's pass on to some explicit examples. For example, you take the particular function sum of squares of the coordinates, take it as a function from Rn to R, and then you want to find out from the first principle how to compute its derivative. Okay, so before we talk about how to compute technically the derivative, when you come to these explicit total derivative formulas and so on, the trick is usually you try to differentiate each of the terms, take the partial derivative with respect to those vectors, and then set it in the coefficient at the particular variable, and then put it in in front of the first variable and then keep on adding them. Well, this is not a foolproof formula, of course. You'll see it more rigorously later on. But let's try to expect that if I differentiate the first term with respect to x1, I get 2x1, plug in at the value a1 at that, I get 2a1. I put it as a scalar in front of x1 and I do it for all the coordinates and I write this up. My claim is this is going to give me the derivative of the function which I started with. Okay, so first of all, you need to immediately see, which is almost more or less clear from this expression, that this function actually is a linear map. Okay, you can easily check this. And then I need to use the definition of limit to prove this. This is exactly the derivative. So what I do is, remember, my expression was this particular term, which I would invoke the limit later on, but I need to analyze that first. Okay, so if a plus h is nothing but this particular expression over here, the coordinates of a plus h are pointwise sums of the coordinates. So this is a1 plus h1. The second coordinate is a2 plus h2. The nth coordinate is n plus hn. So I get the sum of the squares of those. And then fa I subtract over here. And then the last linear map, I compute it at the point h1, h2 up to hn, which is this particular term. This itself says that a lot of bad things are kind of cancelled. So you open up these squares, just remove the first term after you open up the square. The second term of after opening up the square, what you end up getting is just h1 square plus dot dot up to hn square. So this, if I just divide by this term, I simply get some square root like this. And if I compute a limit of this particular thing, it's more or less clear to see that this converges to 0 as each of these coordinates converge to 0. So this immediately tells me this is guaranteed to be the unique derivative of the function f at this arbitrary given point a1, a2, an. So instead of this, if I have taken the origin over here, immediately you should conclude that the derivative is 0, which is usually expected in if you take n equal to 1. If you take n equal to 1, the function become f x1 goes to x1 square, and the derivative at the origin is 0. So therefore, this kind of nicely generalized to higher dimension. Okay, there are some examples I have computed over here, which you can go through. So for example, if I take a function with independent coordinates, so what does it mean? You take a function g of x1, x2, xn, but the only point is that in each coordinate is only dependent on that particular coordinate where it's coming from. So you have n many functions, f1, f up to fn. The first coordinate depends only on x1, second coordinate depends only on x2, nth coordinate only depends on xn. Most trivial example you can imagine over here is the identity map, which obviously satisfies this. And then you see, if you take the whatever roughly you have intuitively imagined, you take the derivative of the first coordinate with respect to x1, you end up getting something like this, evaluate at a1 and multiplied with x1, and then set it in all the coordinates. You end up expecting something which should be the derivative. And indeed, you can go through these details where you can check that this is indeed true. Third example is the affine linear functions. So, for example, as I have told earlier, the linear maps are also differentiable at every point. So, a generalization of slight more generalization of affine linear maps. Linear maps are affine linear maps. What you do is You take a linear map L and take a constant, fixed constant, and you pointwise add it. So my function look like Lx plus C naught, except this first part is a linear term and I translated it by this quantity. So here you would expect that the derivative coincide with the linear term. Well, this is again some kind of pictorially clear when you were looking at the pictures of derivative in terms of calculus. That let's go to that picture over here. So here the derivative was the tangent at this particular point A, FA over here. This is what you expect as the linear map, which is the derivative. But now this is being translated. What you would do is that if you want to talk about this being a linear map, this doesn't work because this is a translation of this linear map. What you would do is that you bring it, push it down so that, push it down parallelly so that it passes through origin, and this is what you expect it to be linear map. So the same principle pictorially happens over here. You take the affine linear map, you use a definition of derivative, you should expect that the linear part of this should turn out to be the derivative of this. Okay, so let's try to see these explicitly. This is very easy to see. In this particular expression, because f is affine, now if you just plug in these values, the C naught turns out to be cancelled, and my L being linear, I can just open it up. So everything gets cancelled on the top, and this limit therefore should be 0. So if I just set in that LH as a factor over here in the definition, this gives me that this limit is 0 and L is already a linear map, and I already know that derivative must be unique. If this particular linear map satisfying the definition of derivative, so this L itself should be the derivative of this. So what does it say? It says that f prime A should be the linear map L for every point A. Okay. Again, another interesting result should be the derivative. If the function is differentiable at a point A, then it should be continuous at A. So what you would do is that you try to approximate this particular term, which is the difference of this, so that if you apply the limit to this fa plus h minus a, it should go to 0. In a sense that if I want to prove f is continuous at a, it's enough to prove limit h tends to 0 of f of a plus h is simply equal to fa. Okay, so I have to work on this particular factor over here. So what I would do is that I'll just subtract this extra term over here, because I would be using the definition of derivative, and then I simply divide by the scalar. So the top term over here, the numerator term, is still a vector, but you are dividing by a scalar, that's allowed, and you multiply by the scalar. This dot is just the scalar dot, and then you adjust this term f prime a at h, so to make sure that this is equal to the left side. Well, if you have done it, now you can apply the definition of limit. But if you do this naively, so what the problem would be is that you have to use a triangle inequality. This two no more would be equal rather. So if you pass to the limit h tends to 0, the norm of the left hand side should be less than or equal to norm of this one, the first factor over here, plus limit h tends to 0, norm of the second factor over here. Okay, I would be able to break the first one into two terms, limit of norm h times limit of this. So there is a small typo again over here. So this should be the bold H, which is a vector still, it's not scalar. And then I should be able to break it into two parts because both the limits actually exist. Okay, but if I do this and then I allow this limit, I pass the limit individually using the limit algebra. This term is 0, so this forces the first one to go to 0. The second one again should be 0 because of the linearity of f prime a. Remember, I have proved that if we have a function which is linear, this function is continuous at every point. Now, if I take just treat this f prime a, if you imagine a little bit, this is a function over here. You are evaluating that function at this value h. Okay. So the continuity at 0 says that this function evaluated at h, if I just put the limit as h tends to 0, this should be 0. So therefore, if I just put the norm over here, this limit is also 0. So what you end up getting is the right side just vanishes. So the left side should therefore vanish because this is a limit of non-negative terms. Again, it immediately implies that the limit exists and hence the function is continuous. Okay, so far is there any questions? Can you please ask if there are any questions so far? Am I audible, by the way?
Yes, sir.
Okay, great. Yeah, so it sounds like everything is silent at my end. So I was wondering if I'm audible or I'm the only person sitting here. Okay, so let's go to the last part of this lecture, which is called chain rule for derivatives. And this is kind of would be important because in tomorrow's tutorial, if you want to compute derivatives of certain functions, this is very important. Okay, I might not go through the entire proof because this is slightly technical and long, and time is almost up. So I'll go through the proof, the sketches of the proof and how I'm going to do it. So the chain rule says, as like the usual chain rule for derivatives in case of calculus, you take one set inside Rn, another set in Rm. So first function I am trying to think of is from A to Rm. And then if I want to apply the chain rule, it means basically I should be allowed to compose with another function. So the second one, what I take is B2 sum R power P, where I have the condition that if A is contained in B. Okay, so under this condition, if I assume that f is differentiable at A and G is differentiable at FA, then this says that the composite function GOF is differentiable at A, and if I want to know what is its derivative at A, this simply can be written as follows. So remember, my f prime A represents a linear map from Rn to Rm. So if I start with a function f from A to Rm, the derivative turns out to be a function from Rn to Rm, the full domain Rn to Rm. Okay, now I am assuming G is differentiable at Fa, then its derivative at Fa should be a linear map from Rm to Rp, and therefore those two linear maps I can compose. So the chain rule basically says that if you want to make a complicated derivative, then it's enough to just compute the individual derivatives at those particular points and compose them. The composite linear map, whatever you end up getting, is going to be the derivative of the composition. Okay, so a short sketch of the proof. How do I do this? Is as follows. So what you end up getting is that you want to verify the definition of limit for this particular function, the composition function. Okay, so this says this is equal to this composition. So you should be able to replace in the definition of derivative this linear map G prime Fa composed with F prime A instead of this one over here. Because of the uniqueness, again, it proves that this linear map turns out to be the unique derivative. So towards that, what you need is try to focus on, because I am taking the general sets A and B, not the entire Rn or Rm. So you should try to fix a certain neighborhood where you want to work on. So this is done in this particular picture. So I need A to be an interior point of A because my limit should exist, and well, f is continuous at particular point A. So I should be able to focus. I need the function value of fa exist and the limit of fa, limit of fx at x approaches a should exist. So therefore I need a to be an interior point. So I take the first delta neighborhood of a. This particular ball over here might go to something weird over here, but if I assume again, just okay, so this is going inside that particular ball over here, that comes from the definition of continuity. Given an epsilon positive, there should be a delta positive, so that the delta ball around A maps to the epsilon ball around Fa over here. Okay, so once you do this, the first approach you do is that you try to estimate the term which is the difference of a f of a plus h and fa, and try to estimate what happens to this term if I just take the norm of it and divide by norm of h. So the first step is to show this norm of this divided by norm of h is a bounded term if I take some deleted neighborhood of 0. Okay, because it's some deleted neighborhood of 0 and this delta is in my control. For example, given any epsilon positive, there was a delta, but I could have chosen some smaller delta and that would still work. So if it's possible in some deleted neighborhood of 0, I could have shrunken this delta and get another smaller delta where it should work, where this term would be bounded. So I could as well assume this is bounded in this particular delta neighborhood of 0. Okay, so this is done over here. And then you try to do the same thing for the image function. Okay, so let's just go through a little bit because I would be able to express this nicely over here. So you try to manipulate over writing a function called f of h. How do I define this? This term over here subtracted with the derivative computed at h. Remember, this is the, without the norm, this was the term that appeared in the derivative, and I divide by norm of h. So this, I would expect that this term should go to 0 as h tends to 0. Well, not just this, I would apply the definition, because this definition does not make sense if h was 0, because I would not be able to divide by 0. So just by brute force, you define at h equal to 0, the function value is a 0 vector. And then you prove that this function f is continuous in this neighborhood of 0. Second is you do the same trick when you apply, go translate it to the second domain. When you go to apply f, everything is translated via fa to some certain quantity, and then you simply define as epsilon neighborhood of 0 over here, and that should work. Okay, after all this thing is done, there is this is kind of very complicated expression it looks like, but what you want to do is that you want to adjust this particular term over here. Okay, so after all these calculation, what you end up getting is some kind of adjustments like this, so that g of fa plus h minus g of fa, and then you look at this particular linear map applied to h. Remember, this is what we wanted to do. G of f should be have derivative at a being this particular linear map. So I put it here. Divide by norm h, you get some complicated expression like this. Now over here, I have G prime at Fa is a linear map. So as h norm of h converges to 0, this term would vanish in this deleted neighborhood. Secondly, I have already in the second term over here in this right. So what I would see is that norm delta h by norm h, I have already bounded it because my G is kind of continuous around the origin. So I would expect over here that I am multiplying a continuous map, looking at it, and apply H by some uniformly bounded term, which is norm delta H by H. So the second term also would converge to 0. So the entire right side would converge to 0 as H approaches 0. This is what I actually needed. Okay, so I have written down all the detailed proofs over here. So in today's lecture, there were not many typos. So I think you can go through this proof. This proof I have taken from this analysis on manifolds from Munkres. More or less it's identical, except I have just added a few lines to make it clear. Okay, I think I am done for the day. If there are questions, let's start some discussion.
Good evening, sir. I have one question.
Yeah.
So in the definition of that limit that you have defined earlier, why we need the point to be an accumulation point? Can we replace that condition with the thing that the point is an adherent point of the set?
Okay, so there was a technical difference. So adherent point usually means the limit point, and accumulation point is just adherent point means you include that point itself to be thrown in the whenever you are taking the neighborhood, and limit accumulation point means you take the deleted neighborhood of that. I think if you look at the definition of limit, what you need is the function need not have a value at that particular point. So this is a technical point. It is already you have seen in the definition of limit in calculus. So what it enforces is that I don't need my value of the function to be defined at that. Even without that, I can define the limit. So for example, you take a function. Let's take a straight line function, some kind of, let's say y equal to x. And at the point, let's say around a point, you just remove the graph of the function and define it, dilate it so that the function becomes discontinuous. So you have seen at
Okay.
that situation, you define the limit still exists. And the value of the limit is as it was before you deleted, adjusted the function like this.
Yes, yes, sir.
Well, that means the function become discontinuous at that point, but the limit
Yes.
still exists. So,
Okay.
but if you just be careful at that point, you see that you don't need to know what happened exactly. My x is equal to a. So
Okay.
there is an idea called left hand limit and right hand limit. When you approach, I don't need to know what happened exactly at the point x equal to a.
Yes, sir.
I could have completely removed the function value at particular point a. I
Yes.
can define the function is defined on the entire real number, deleted that point. But still the
But, sir,
definition of limit should work.
but someone got confused with the fact that suppose I have defined a function from a set, which is
Huh.
a set of a real line. Suppose
Right.
that subset is interval 1, 2, 3, union singleton 5.
1, 2, 3. Okay. The open interval 1, 3 and union
Interval
5.
close 1, 2, 3, union singleton 5.
Ah, okay.
Suppose I have defined this function. then as per our definition, which you give in today's lecture, we cannot
Hmm.
define we cannot find a limit as x is going to 5, because 5 is not an limit point of the set.
Yes, this is not a limit point. This is not. This is an isolated point on a set,
Yeah, yes, sir.
completely
This,
outside.
yes.
Yeah.
But if we could have assumed that the limit should be taken if the point is an adherent point, then we could have find the limit at this point 5 also.
Absolutely. Yeah, yeah. So, but that
And
is kind of little weird in sense of
in,
calculus.
in that case, sir, what would be the limit? Suppose the
So,
function is fx is equal to x.
okay, but here you see that around 5, I don't have enough supply of points except
Yes,
for
sir.
this point 5.
Yes, sir.
So usually if you define something like limit, you expect that even if the point is not there, I should have enough supply of points so that x approaches to a makes sense.
Okay. Okay.
So how
So
do you
can
avoid that?
can I say in that case x approaches to me to a means x is equal to a because there is not enough
Exactly.
slice.
Exactly. Exactly. So that way you can
Okay.
define its limit. There is no problem with that, but
Okay.
it makes the definition little weird because whatever value you put over there, the limit, there is no problem at all with the definition of limit.
Okay. Okay. Okay.
So
Fine, sir.
in
Thank
some
you.
sense that if you have lots of isolated points, it
Yes.
doesn't matter what kind of definition you use around that. By Yeah, I think limit usually doesn't make sense in the most general setting of topology. But yeah, in case of matrix space, you could have just said it. Or in case if you more generalize it to something called nets,
Okay.
I think this concept still makes sense. Whatever you just said, we don't do
Okay.
it over here just to make sense of our real perception of topology over here.
Okay, sir. And sir, one more question.
Yeah,
In the proof of the theorem that the continuous image of a compact set is compact, I
right.
have one question regarding that proof. Will you please show me that slide?
Yeah, just a moment.
Please.
Yeah, here, right?
Yeah, a small explanation that I want. How
Sure.
A would be a subset of the union F inverse V alphas, where alpha is in I. How A is a subset of this? I got confused over this. Somehow
Is
I
a
missed.
subset of union of F inverse V alpha.
Yeah, yes, sir. This part only.
Um, okay, okay, so let me see. So you take a point of A, then f of that goes inside this, and you take the full preimage of V alpha. That should make sure that this is subset. I mean, I'm thinking very set theoretically.
Yeah.
So F inverse V alpha usually means that you take the full preimage.
Yeah, okay.
So that means all possible points are kind of already covered. You start thinking like this, that you start with a point little a from capital A. So f of that goes in this union.
Okay,
So
F of
f of a goes in some V alpha.
okay.
Now only problem is whether a would come inside f inverse V alpha. But by
Yes.
definition, f inverse V alpha is a full preimage.
Okay, okay, okay.
So a has to be there.
Okay, yes, yes, yes. Fine, fine, fine. No, it's
Yeah.
okay. It seems to be yes, sir.
Yeah,
Thank you.
set theory sometimes is very confusing.
Thank you, sir. Thank you so much.
Sure.
Yes, any other question? Okay, so today the matter presented over here basically on the topics limit, continuity and differentiability from Rn to Rm. So I hope you enjoyed the way Dr. Siddharth Sarkar elaborated. Uh, if any question, then ask. Otherwise, let us clap and say thanks.
Yeah, thank you.
Thank you, sir.